Hello, my name is Brent Young. I'm from the University of Auckland in New Zealand, and I'm going to present to you my virtual poster on process digital twins for sustainable geothermal development and management. Now, let me share my screen and show you my presentation. So my colleagues, Wei Yu, in the department, and this work is based upon our students' thesis, PhD thesis, Dr. Mohammed Dabur. So in this talk, I'll very briefly introduce the concept of digital twins and then show a couple of examples where we have applied these in practice in a geothermal power generating setting. One, where we've done dynamic modeling of surface facilities to look at the plant and comment on such things as redesign of fan coolers. And two, to look at coupling reservoir models with plant models for estimation of the future life and operation of the asset. And then we'll conclude with some final comments and talk about our future work in the space of Ahu Ora. More on that later. So digital twins in theory, I'll be talking about this in my subsequent virtual poster, but the digital twins is a relatively new term and has come to mean the application of digital models that are behaving like, looking like, and connected to the real world. And so it goes beyond a digital model simulation and to the full digital twin, as sort of shown here on the slide. And what I'll be describing today is perhaps a step towards these digital twins in geothermal processing, where we have developed validated digital models and use these to effectively shadow the plant and plan for activities. So first up, you must create a dynamic, or digital, it doesn't have to be dynamic, it could be steady state, but a digital model of the process. So in this case, we were actually modeling a real organic Rankine cycle plant in New Zealand, where we're using the organic Rankine cycle to assist us with power generation from a geothermal field. Of course, developing a dynamic model itself is a complex task, but it's perhaps not new in itself, although this model itself was quite new and was used to test various different control schemes. We've previously published on this work elsewhere. So what does the dynamic model look like? Here's PFD from the simulation software SYMMETRY. And with this, we were able to, pretty much out of the box, get a reasonably accurate model of the power plant. We got within about a megawatt of the 20 megawatt or so output that this plant was generating. And here you can see some real-time signals being fed into the simulation digital twin or digital model, and comparing that with the gross power output. You can see there's a consistent bias, but it's relatively small, and mostly following the gross trends of the plant. Again, that is detailed explanation or is given in the geothermics paper referenced. We use this model to actually advise on the design of the cooling fans and what we needed to do in terms of adding more or operating them better. The slide here describes some of the thought processes that one can indulge in, and the thought experiments, if you like, backed up by the digital model, digital twin that we were using. Again, Proctor's work describes this in more detail. So this is kind of a digital model use, or a digital twin, where we're using the model offline to assist us with questions about design and operations. So here we looked at the data from the area, looking at air temperature, and actually looking at adding in different numbers of fans and whether it was worthwhile from a cost-benefit analysis. We can see here actually the payback's not too unreasonable. For a plant like this would actually could relatively be something that they could actually consider. So a more complex digital twin was developed in the major study that I'm going to talk about today, was where we were modeling the reservoir as well as the facilities. So the generating power station as well as the reservoir itself. Quite a complex cycle if you think about it, but again, great applications of engineering, chemical engineering at its finest, if you like. So how do we do this? Well, we coupled our simulation of our facilities, which just mentioned before, which is coded in SYMMETRY, with a simulator of the reservoir in the TOUGHZ simulation software. And through a Python bridge, we're able to take well input and output flow data from the reservoir to the process model and then back again. And so therefore we could get quite a detailed picture of how both the reservoir and the simulated the process could change over time. So I guess the addition of the reservoir also means we need to consider the complexity of the digital twin of the plant as well. This included pipelines and valving and so forth for the production wells, the wellhead itself, and the pipelines. There's several kilometers of pipelines to be considered, so it was important, but also the injection wells. And similarly, there was kilometers of pipelines to consider. As mentioned before, the reservoir model was developed in TOUGHZ, and this communicated with the SYMMETRY model of the process. These were the conditions shown here. We had 3 production wells and 3 injection wells, and a relatively well-studied field. Looking over time, we tried to couple the dynamic model and the reservoir and match it with what we were seeing from the plant and the reservoir. And here we see power output over 2 different periods of the year. Basically the month of January and the month of July 2018. And you can see here that the plants and the digital twin are tracking pretty well with the simulated power. In the summer, we're actually able to get quite a good match of the dynamics with perhaps a slight bias, again, within a few percent. on the winter, we didn't have the some of the ambient data near us that fell out of the data set through a sensor failure. So, but you can see here, we're still modeling the general trend through the of the actual power and output, which is really what we were wanting for this particular model. Because what we wanted to do is look at this model, use of this model for well optimization, and doing an optimization look ahead over time, years into the future. The assumption on how this plant is operating is that you can almost set and forget it. Don't want to invest too much time in things. Don't want to change the way we choke the wells, etc. But unfortunately, this is just not the case in terms of getting the most out of the field. So what we found is that over time, if we can, and here we are projecting, many years into the future, and future life of the field, that we can actually, through judicious choking back of the wells, we could actually understand better how the reservoir and the plant is communicating through the use of this validated digital model, and optimize so that we could actually continue operating at our desired power output over a much longer period than the standard plant conditions would indicate. You can see that very much that decline on the right-hand figure here. So, there was a number of conclusions that we could make for this in terms of detailed operation of the plant and how we could actually operate this in the future, and to actually optimize the power generation until we, and even delay the costly drilling of additional wells in the future. Overall conclusions that that we could use it to help with the economic viability of the plant over a much longer time span, and we've described in very briefly the application of digital shadows, if you will, to the geothermal industry in New Zealand, and point to how they could be used. But it's fair to say that the full-blown digital twin is still very much in the early stages of development for the geothermal industry. I'd like to finish off by acknowledging the two former PhD students whose work this presentation is based on, and my other core authors and collaborators. Thank you very much for your attention.